So in this video, we're going to learn the derivative rule for a to the x when a is a base other than e. And so this will require you to think about a couple of properties that you hopefully recall from your pre-calculus college algebra days. So let's start off for a little motivation of this rule. And so I'm starting off with, let's just say let y equal a to the x. And of course, I'm trying to come up with dy dx. But first I want us to rewrite a to the x. So I can rewrite a to the x, or really anything, as e to the natural log of a quantity. So inverse properties of e in natural log says e to the natural log of a quantity is just that quantity. So I'm rewriting this as e to the natural log of a to the x. Well, I have a property of log, so just focusing on what's in that exponent, that says I can bring x down as a multiple in front of that natural log of a. And now I really want you to think about a is a number, so it's just a constant. So I want you to think about how, in fact, I'm even going to rewrite this and say, okay, this is my natural log of a, where natural log of a is just a number, so natural log of a is just a number times x. So just kind of think of it that way. Okay, so now if I wanted to find my derivative here, and working with that last form, the derivative we know of e, derivative of e to a function of x is going to be e to that function of x. So I'm kind of working with that last form there. So this right here is, of course, representing, with the chain rule, the derivative of the outside function. And then times, and I need to represent then what is the derivative of the inside function. So with an exponential function, the inside is what's up in that exponent. So in this case, what is in the inside is what's up in that exponent. So that's the inside. Well, the derivative of a constant times x is just that constant. Derivative of 7x is 7. So the derivative of natural log of a times x is just going to be natural log of a. Well, now if we kind of just work our way backwards, e to the natural log of a times x, go backwards along this whole line of thinking that we had in the beginning, that's just a to the x. So what do I now have? I really just have here a to the x times my natural log of a. So that is our derivative rule. Typically we write it in the other order, natural log of a times a to the x. But that is our derivative rule for the derivative of a to the x, where a is a base other than e. All right, so this is going to be natural log of a times a to the x. And notice that this would work for e to the x. Like this is the more general rule. If you think about, your derivative of e to the x with this more general rule, it would say it's natural log of e times e to the x. Well, natural log of e is 1, so, oh, yeah, okay, that would still work. So this is sort of the more general rule. All right, now, every time you learn a new rule from this point forward, you have to think about what it's going to look like in conjunction with chain rule. So I'm always going to kind of write that off to the side. So the inside of an exponential function is, just like with e to the x, the inside is what is up in the exponent. So the f of x in the exponent. So if that's more than just a plain old x, the derivative of the outside, well, my derivative rule says derivative of a to the x is natural log of a times a, but now it's with the inside function left alone. So times a to the f of x. And so this portion, this is your derivative of the outside. And then, of course, as always, it's times the derivative of the inside. So times the f prime of x. So that's what your a to the x rule looks like written in conjunction with chain rule. All right, so let's just look at a couple of examples here. So number one, let's just let f of x equal 5 to the x squared plus 2x. And I didn't write any directions, so let's just say, of course, we're just finding f prime. Alrighty, so let's do it. So we have the outermost structure with the chain rule version of the rule that I wrote on the upper right up there. So the derivative of 5 to a function of x, that outermost rule says it's going to be natural log of 5 times 5 to the inside function left alone, x squared plus 5x. So again, this is my inside function. Then by chain rule, it is times the derivative of that inside. If the derivative of the inside is more than one term, which it is, you need to have parentheses around that. So our final answer here is really what we have written there. I don't know that there's much of a better way to write that. You can write it in any order you want. So if you wanted to say 2x plus 2, you could factor out, I suppose that's one thing. Let's do that just for the heck of it. One thing, if you really were so inclined, you could factor out a 2. So just to show you, you might see a different way to write this. If you factor out a 2 here, then you could think of this as 2 natural log of 5, and then times the quantity of x plus 1, and then times our 5 to the x squared plus 2x. And so this is kind of interesting because sometimes what books will do is like with that 2 natural log of 5, they'll say, oh, well, I could make it look maybe kind of nice and bring that up with my properties of logs and think of that as natural log of 5 squared. So we could call this like natural log of 25 times the quantity of x plus 1 times 5 to the x squared plus 2x. I don't know. So, I mean, honestly, the first form was fine as well, really. So I'll circle that as well. So this was just fine too. All right, so that is an example of just kind of working with this one. Let's look at another one here. So one more. Number 2, suppose I say let's let f of x equal 4 to the g of x power. And let's also suppose that you're told that g of 1 is equal to 2 and g prime of 1 is equal to negative 3. And you're asked to find f prime at 1. So this is a type of question you may see from time to time, whether it's with this particular rule or some other rule, derivative rule you're working with. And that's going to be where you kind of have to find a derivative somewhat in general, I would say, and then sub in particular values given maybe a list of ordered pairs that satisfy a function or its derivative, or maybe you have to get this information from a graph or something along those lines. So let's take a look. Sorry, that looks so sloppy. I wanted to fix that. Let's take a look then at looking for our f prime. First, let's just write out f prime of x. So once again, we have a similar structure as the last example. We have 4 to some function of x. So our new derivative rule for this says that this is going to be natural log of 4 times 4 to the inside function left alone, g of x, and then by chain rule times the derivative of the inside. Well, that is going to tell me that if this is my structure for f prime, then f prime of 1 just says go into this function, and every place where there used to be an x, we're just going to sub in 1. So that's all I'm doing there, just replacing x with 1. And now I should be able to use some of the given facts here. So 4 to the g of 1 is given to be 2, so 4 squared, and then times g prime of 1, and that's given to be negative 3. So what do I really have here? I have my negative 16 times the 3 is going to give me negative 48, and then I still have times my natural log of 4. So we'll just leave it like that. So that's a new rule for us. So that's our derivative of a to the x. So next time we'll come back and wrap up with just a couple more examples with the chain rule.